Okay, so the plan for today is to start in the chapter three, and chapter three is all about numerical descriptive measures. So we talked quite a bit in chapter two about graphical descriptions, um, graphical descriptive statistics. So we have a big data set. We want to make a picture to try to convey some aspect of that data to our audience. And chapter three is about a similar idea. We want to take a big data set and make it more comprehensible for our audience, and looking at doing that through numerical descriptive measures. So that's what we're starting into today in chapter three, and starting with 3.1 measures of center. Next week, we'll probably finish up 3.1. We probably won't get through it today. So next week, finish 3.1 and then start 3.2 measures of variation. Just kind of a heads up, measures of variation, the computation of some things like variance and standard deviation are fairly computation heavy. Um, so that might be a section that you might want to, read over beforehand, maybe work a couple of practice problems, and then, come to class, work through the problems in class, and then do even a couple more practice problems afterward. It's one of those things that it looks very daunting at the beginning, but after you do it a few times, and I'll kind of show you the process that I prefer to go through, um, I think after you do it, the calculation 5 or 6 times, it's a little more straightforward. The quote of the day today is kind of more of a couple of related ideas than a direct quote, but just the idea of making strategic use of the learning curve. Um, so I think most of us have heard of something related to this idea that there's this learning curve idea that, and this can be kind of interpreted a couple different ways, but when you're just starting into a new subject, on one hand, it's kind of difficult to get momentum going because you kind of maybe feel a little inadequate. But on the other hand, when you first start into a subject, you're learning an awful lot in a given unit of time. But once you kind of say reach an intermediate level or say advanced beginner level, if you spend that same amount of time, your yield is lower. And once you reach an expert level, you have to put in an enormous amount of time to get even a little bit of yield. Uh, so there's kind of a sense in which, if you want to become the world authority on a certain topic, some tiny subject, you have to put in an enormous amount of time and effort and work and cognition into that one little field, in order to get your expertise that high. So that's like the, master of one trade. It's often better to be a jack of all trades in some sense. I know there's the, jack of all trades is a master of none kind of dig at the jacks of all trades, but um, maybe there's some balance there. Maybe we want to be able to, think of having broad coverage over a lot of areas, and then the ability to go very deep, not very, very deep to the, point of like foremost expert in the world, but being able to go pretty deep to say an advanced level in a few different subjects. And I think it's easy to focus too much on one or the other, right? If you focus too much on the breadth, you might lose out on having the advanced skills. You might, say you want to go into engineering. Well, it's going to be really important that you're really good at engineering to say pass the PE exam and get a job in that field. But on the other hand, it's also probably pretty important to know a little bit of coding or maybe a little bit of finance even, right? Like, so having a wide breadth where you have invested a little bit of time into a lot of different subjects and gotten those very high yields at the beginning, you know, even, 25, 50 hours of work in a certain field can get you an awful lot of understanding of that field that you didn't have before. Certainly nowhere near an expert in it, but you might understand that field, or where those folks are coming from a lot better, and at the very least know when to seek expert advice from somebody in that field. And then you want to be the expert that people will turn to. That's the marketable skill that you bring to the table. Um, so I think that it's important to kind of balance this learning curve idea. If you kind of throw all your eggs in one basket, that's a bit risky, right? If you're if you were the best DVD player repairman in the world, 15 years ago, uh, that's probably not such a desirable trade these days. And then kind of related to this idea is um, kind of an idea that a mental model that I've come up for different types of knowledge, and not saying that one is better than the other. Of course, I have my personal preferences, which you'll probably see in a minute here, but I think of these kind of four quadrants of knowledge. And in particular, one aspect is the time constant. Um, so if I learn a thing or if I master a skill or whatever, how long is that good for? How long is that relevant for? Is this a very dynamic area or field, or is it more static? Right? If I learn a mathematical theorem, if I learn how to, say, compute the standard deviation, that's not something that's going to change in the next year or 5 years or 20 years. The standard deviation is always going to be the standard deviation. On the other hand, if I, watch the football game this past Sunday or this coming Sunday and and there's this cool play, I can talk about it around the water cooler this week. But if I bring it up, a month from now or 2 months from now, unless it was a very, very strange thing, people aren't going to really care about it, right? That the value of that knowledge goes to zero pretty quickly, where the value of some more static knowledge stays around longer. And then there's also this kind of idea of foundational versus trivial. In other words, if I learn a piece of knowledge, is it kind of isolated from everything else I know? It doesn't really have connections, doesn't really inform my current mental model very much. I just know this extra piece of knowledge. Or am I able to tie it into things I already know, give a new perspective on things I already know, and build off of it in the future? So trivial versus foundational. And of course, my bias is probably in the static and foundational world, being, someone who is interested in math, who teaches math, who likes to study math. Um, these are typically foundational concepts. We build up an idea and then we build off of that and we build off of that new idea and so on. And these are static concepts. And there are, certainly benefits to being in this field. I personally don't really like the dynamic trivial quadrant, but there's a lot of usefulness in the dynamic trivial quadrant as well. Things like, say, IT support or things like accounting. I mean, these are fields that if I worked in them, it would drive me crazy. But, a lot of folks like that challenge that, oh, Microsoft came out with a new update to Office. Well, now I've got to figure out, like, what are all the changes? What are all of the, if I used to know where this thing was located, this, data analysis tool pack or whatever, they came out with an update. Well, now I need to relearn where it's located. To me, that feels like spinning my wheels, but a lot of people like that challenge of kind of staying up to date with things. Or accounting, right? The tax code kind of changes a little bit every year, and you've got to stay up to date with those. And those people certainly bring value to the table, right? Because of people like me who don't want to put in the time and effort to keep up with that. I want somebody to be able to call and say, hey, my computer's broke. How do I fix it? Or, hey, I really don't want to do my taxes. Here's all of my papers that all these people sent me, make it go away. So there's absolutely value there. I don't mean to say that any of these quadrants are good or bad, but think about your personality and your preferences and whether they align with the type of field that you're going into, right? Um, okay, so that's kind of the thought for today. So moving on to section 3.1, measures of center. We have lots of measures of center. Some of the most common are the mean, or that's what statisticians make a big deal about calling the average. They call it the mean. The median is another very popular one. A weighted mean we see an awful lot, even if, in some contexts, we don't specifically call it a weighted mean. We'll see that it's an example that I think you're all familiar with. Some others that are used in more specialized cases like geometric mean, harmonic mean. If you're in engineering, you might see something like root mean square. There are lots of different types of means, lots of different types of measures of center. So what is the goal of a measure of center? if I compute a number and I say this is the measure of center and I'm going to report to you a number that's a descriptive metric of a given data set, what is the piece of information I want to convey to you? Well, I want to convey something along the lines of something like, what does the typical data value look like? Right? If I'm looking at a data set of 1,000 heights of people in Pittsburgh, a sample data set, I don't really want to look over 1,000 different heights. That's going to be confusing for me to interpret. But I might say like, okay, what is a typical height of a person in Pittsburgh? You might say like, well, 5'9"-ish or something like that, right? Now, this is a pretty loose question. It's not very specific, and that's why we have lots of different ways to answer it. We have lots of different approaches to address this question. What does the typical data set, data value in the data set look like? We have a few data sets we're going to work with really throughout the next two sections, really kind of throughout the next three sections, but mainly the next two sections. The first is a list of salaries. We're thinking of this as sample data. If I just gave you this list and told you they were salaries, you wouldn't know whether it's sample or population, but I'm saying here that it's a sample. So just making that very clear. And we're thinking of this, maybe we're interested in the salaries at a big corporation. I'm wondering, okay, what do people make there? Maybe I'm a recruiter, or maybe I'm interested in a job there, and I, stand outside the front door creepily and ask the first 7 people I see, how much do you make? And if they don't get offended, they tell me how much they make, and I write them down, and I try to make some kind of estimate of maybe whether I want to work for that company based on what I think the typical salary would be. Is that in line with the salary that I'm asking? Or we have these two data sets, the Ashley data and the Brandon data. I always use the same names, so I'm sorry if anybody is named Ashley or Brandon. I don't mean to call anybody out specifically, but I just always use these because it's A and B. We're considering these to be populations. Again, if I just said these are tax returns per day and here's the information, you'd have no way of knowing just on that basis, just on this list of numbers for each of them, whether that is supposed to represent a population or a sample. But I'm just telling you explicitly here, this represents a population. And these are tax returns completed per day for, say, 2 people who are maybe, interning at an accountancy firm around tax season. So again, what does Ashley's kind of typical day of performance look like versus what does Brandon's typical day of performance look like? We see that Brandon has some really good days and also some not so good days where Ashley maybe just at a glance is a little bit more consistent. We can glean information like this when we have a data set of size 5. That's not too bad. But if you imagine we had a data set of size 500, this is much more difficult to do. So that's why we're leaning on these descriptive measures. You might say it's a bit silly to, take data sets of 5 or 7, size 5 or 7, and compute, 7 different means or something for them. We're giving as much information almost as was in the data set to start with. But again, we're using these as examples. We would typically be imagining that we're applying these measures to much larger data sets. But obviously we're using smaller data sets so we can work through things by hand and it's not too cumbersome. One note on chapter 3, I did mention it last week a bit as kind of or last class a bit as kind of a tangential comment, but in chapter 3, because we're going to be doing more computation, and we talked about this when we went through Excel, you can sometimes lean on Excel for the heavier number crunching. So particularly in chapter 3, my kind of rough recommendation to you would be, if you're being asked to compute a measure of center, if you're in section 3.1 and you have a data set of size, 10 or so, maybe up to like 15 or 20, and you need to compute something like a mean or a median, it's probably best to do that by hand, to get the practice doing it by hand and to kind of understand how all these computations work. If you have a data set of size 15 or 20 or larger, or if you have a data set where the numbers are really nasty, you know, if it's like 1,352.47 or something, if all your numbers look like that, I don't want to, you know, add up 15 of those. That's going to take forever. That's where you would lean on Excel a little bit more. So we'll be talking about how to do these computations by hand, as well as how to leverage Excel for these computations. So just a little note on that. And then when we get to 3.2, just in case I forget to mention it, for variance and standard deviation, I've already mentioned that those calculations are actually pretty cumbersome. Once you get up to, you know, past maybe 5, 6, maybe 7 data points, that's when I would transition to using Excel instead of doing it by hand, or when you have 5 data points or something, but they're like, you know, really nasty numbers, like, you know, 4, 5, 6 significant figure or something like that. So, you know, so 3, 2, I would set my barrier for when to flip over to Excel at maybe about half the level that I would for say 3, 1. But for both of these sections, most of the problems should be doable by hand. And typically there's a few of them at the end, maybe 2, 3, 4 problems kind of near the end of the homework set where you'd say, okay, yeah, this is one. I'm going to jump over to Excel and let it do the number crunching for me. So just a quick side note on that. All right. So a little bit of notation for chapter 3 and really kind of for the rest of the course. We're going to suppose we have a data set and we have data points x1, comma, x2, comma, x3, and so on through xn. So here we have some variable that we're interested in, maybe like heights of people in Pittsburgh. We're going to think of x as representing that variable. And then we're going to think of our data set as consisting of data points. This is like the first data point, so the first person whose height I measure. This is the second person whose height I measure, the third person, out through n. So when we use n in statistics, that letter is usually trademarked for sample size. Almost all the time. I would say that if it's not being used for sample size, that ought to be made very clear from the context. But if I see an n, I'm thinking sample size when I'm in statistics. Now, an important note is that each data point has a value. So maybe this person is, what's 5'5", like 65 inches. Let's just do it in inches. Maybe this person is 66. Maybe this person is 65. These are 2 different data points because they represent 2 different people. That's like the worst arrow of all time. These represent 2 different people. They're 2 different data points, but they happen to have the same data value. So I have n data points. Each data point is representative of one individual in the population or the sample. Each data point is associated with a data value. So even though we have in a data set, we have distinct data points, I shouldn't be sampling the same person over and over again, at least not at this point. We will talk about things like sampling with replacement a bit later, but at this point, we're kind of leaving that aside. So these represent different people or different individual elements of the population, but they could have the same data value. So if I'm doing something like computing a mean, I don't want to say, oh, well, 65 occurred here and here. I'm only going to count it once or something. No, that represents 2 different data points. They just happen to have the same value. So I will try to be careful about the distinction between a data point that's like an individual in the population or a sample versus a data value, which is their measurement. So a data point might be this person, their height, where the data value will be the height of that person. It's a little bit of a subtle distinction, but it is an important one. And also, when we set up our data set like this, we're basically going to always assume that it's ordered. There are a couple exceptions to that, like when we don't have ordinal data, but for the most part, typically, when it's feasible to do, x1 is less than or equal to x2, less than or equal to x3, and so on, xn. So when it's feasible to do, when we have at least ordinal data, we'll think of ordering our data in this way before we actually start doing anything. For the mean, it doesn't really matter, but for things like the median, it matters a lot. So we're going to think about ordering our data first. Okay, so what is the mean? The mean, sometimes also called the arithmetic mean, or just the average. But if we just say mean, we typically mean the average or the arithmetic mean. It's just the average that I think everybody has computed at some point in their life. As kind of a little side note, for some reason, folks make a big deal about calling it a mean in statistics and not an average. And the argument is that there are lots of types of averages, which is true, but there are also lots of types of means. So that argument kind of falls flat for me. I'll probably half the time call it average and half the time call it mean. The Excel function that computes it is called its equals average. So, I mean, I don't know. Sometimes I think people make too big a deal of semantics, and a lot of the other times I think people make far too small of a deal of semantics. Just getting the wording correct so that we understand what the other person is saying. I think mean versus average is making too big a deal of semantics. Okay, so what is the mean? Well, it's the average. It's computed as x1 plus x2 and so on, alpha plus xn divided by the sample size n. I take my data set, I add up all of the data values in that data set. If I have repeated values from different data points, I repeat them in the addition. And then I divide by the sample size. And that's my average. Note that to compute an average, to compute a mean, I need to at least be able to add my data up. If my data set looks like, if I'm the fashion designer sitting on the corner writing down colors, if it looks like red, blue, green, green, yellow, well, a mean isn't going to be so good for that, because how do I add those up, right? I need to be able to add up the data values that I've collected. Now we have a bit of notation for the mean, and at this point, this will seem quite pedantic, but it actually is a very important idea, especially starting in, say, chapter 6 and moving on to chapter 7 and 8. But for each of these measures, we have kind of two versions of them in a sense. We have a population version and a sample version. So we have, say, a population mean, and we have a sample mean. Let me actually move that down a little bit. So the population mean, of course, is applying this calculation to the entire population, where x1 through xn, that data set represents everybody in the population, everybody that I'm trying to say something about. Heights of people in Pittsburgh, that would be like all the people in Pittsburgh. Where the sample mean is applied to a sample. I take a sample of size 1,000, compute the mean of that sample data. That's the sample mean. These have notation that refers to them. The population means notation is a Greek letter. It's this letter. Probably more properly called mu, but everybody calls it mu, like M-Y-O-O. Maybe so we don't sound like cows when we're talking or whatever, but mu or mu. And it kind of looks a little bit like a U with a tail at the bottom. So if we had, like A, A, this is what mu would look like. It kind of has a tail that goes down below um, the baseline or whatever you call it, the bottom line of your, kind of like a P or a Q. And it's the Greek letter M. So this is mu, the population mean. Our population parameters, we often write in Greek letters. And our sample statistics, we typically are often write in whatever you want to call them, Roman letters or American letters or English letters, whatever term you want to use. If we're talking about the random variable x, I'm describing my data points as like x1, x2, xn. So I'm thinking of my variable as being x. Then I write an x, the variable under consideration, with a horizontal line above it. So x bar, or I could write, say, like y bar if my variable of interest was called y, or z bar if it was called z. So just putting a horizontal line above the variable that I'm using to describe my data. We say this as x bar. So I would just pronounce it as x bar, right? If we had x bar equals 3, I would just say it that way. And it's the sample mean. So population mean, sample mean. One little note, if we did have, maybe we're in a scenario where we're talking about a few different samples, we might call one of them the X's, one of them the Y's, one of them the Z's. If I had heights of people in Pittsburgh, heights of people in Cleveland, heights of people in Wheeling, I might name them different variables. For my samples, I might do the same thing for population. There, I would refer to it with a subscript, say mu sub x, mu sub y, mu sub z, something like that. Just a little subscript to the right to indicate that this is the mean for this population or that population. So a little bit of notation, kind of a joke. There's a famous physicist, Richard Feynman, who has a quote that goes something like, and yeah, I mean, this is, a funny dig at math. But it goes something like, 90% of mathematics is creating notation or something like that. And there is actually some truth to that. We have a big concept, we create a notation to encapsulate that concept. We can abstract away from that concept a little bit. Very similar to how I think it's actually called encapsulation in programming. We might write a function to do some certain thing, we might write a function to take an average, and then we have this equals average function in Excel that we can just use and forget about how it works under the hood. We just know that it does an average. So I think that's all that I have to. Oh, and one more very important thing. These are computed the same way. So if we have a population, x1 through xn, we compute mu as the sum of the x's over n. If we have a sample x1 through xn, we compute x bar using the same formula. Right. It's just we use one piece of terminology or the other, depending on the situation we're in, depending on the data set that we're representing, whether it's a sample or a population. Now, again, this is where people look at this and say, well, this is kind of silly. This looks like the same thing. Why are we calling it two different things? Well, this is a population and this is a sample. And remember, the idea was that most of the time we're in the situation where what we want is the population parameter and what we have is the sample statistic. And later on in the course, we're going to look at like, well, I have this sample statistic. I would like to know the population parameter. I probably want to guess that the sample statistic is probably pretty close to the population parameter. I would probably want to guess that the X bar that I compute on my sample is close to mu, which I don't know and don't have access to. How close is X bar to mu? Well, to say something like that, I need two different names, right? I need to be able to talk about how close is X bar, the thing I have, to mu, the thing I want. And that's why this distinction is so important. And that's the kind of question we're going to be asking in things like chapters 7 and 8. Like, is X bar a good estimate of mu or not? Or how good an estimate is it? Or things like that. Okay, so let's bring our data sets down. I actually want to kind of do these in the opposite order, so let me just move them around a little bit. And we'll go through each of these data sets and compute the mean for each of them. So we'll start with the Ashley data. And I see that her data set is 5, 8, 9, 11, 7. And I see that it's a population. So I'm going to say that the mean mu for Ashley, and we'll write a subscript A here because I know I'm going to compute the mean for Brandon as well. The mean for the Ashley data is, and let's respect that ordering, even though we don't really have to with the mean because addition is commutative, but we can do 5 plus 7 plus 8 plus 9 plus 11 over an n of 5. And if we do this, we get 11 plus 9 is 20, 7 and 8 is 15, plus 5 is another 20, so we get 40 over 5. The mean for Ashley is 8. If we look at the Brandon data, we compute Brandon's mean the same kind of way. Let's put them in order: 3, 5, 7, 11, 14. And 14 and 11 gives me 25. 7, 5, and 3 gives me 15. That's also 40. And then divided by 5 equals 8. So the 5 came from n, the size of our data set. Each of them had 5 data points in their population. And we see that both of them have a mean of 8. So Brandon has some kind of really good days, but also really bad days, and that kind of balances out. Ashley is more consistent. She never really has a really good day, but she also never really has a really bad day. And then let's think about salaries down here. We see that salaries, this data set is a sample. So let's call it X bar. And if I wanted to, I could, if I had more than one of these, I could name it X bar, Y bar, Z bar. I could also use subscripts here as well, like X bar S or whatever descriptive thing I want. But here I only have one sample mean to compute. So let's just call it X bar. And this is 25 plus 3 28s. And then 30, 55, and 100. And that represents 7 data points. Later on, kind of as a matter of good practice, I'll rewrite them in the correct order. But for now, since we're just doing an easier calculation, I'm just writing this way. This is a little more involved calculation. Let me jump over to the calculator for this. Now, I might be tempted to do something like this. So I have 3 28s, 30, 55, and 100. That looks good. And then I might be tempted to do something like this, right? Well, that gives me an average of 208. I think something probably went wrong here because the average, it should be between the maximum value and the minimum value, right? It's a measure of center. It's looking at where's the typical data point, where's kind of the middle of the distribution. It should be between the max and the min. In fact, we can see that very clearly if in our average calculation, we had replaced all of the other numbers with the max of say 100, I would get 100 added to itself 7 times divided by 7, that would just be 100. So if I replaced all of my data values with the max, then my kind of new average, it wouldn't be a very good average anymore, would just be that maximum value. And clearly, not all of my data points have value equal to the maximum value. And same with the minimum. So my average should be between the max and min, but I got an average of 208. Something went wrong. I've got to be a little careful here. If I do this, the calculator respects order of operations. So it will do 100 divided by 7, get that answer, 14-ish, something like that. And then it will add to that 25, 28, 28, etc. So there's two ways I can get around this. I think the easiest way is to do this in 2 steps. Just compute the numerator, 294, and then divide by 7, and we get 42. The answer to all life's questions, 42. If you've ever seen Hitchhiker's Guide to the Galaxy or read it. I read the book and it gets so much good publicity, but I don't know, it just didn't really resonate with me. It had some interesting ideas. Maybe it's because I've heard of some of the ideas before, but it was kind of an interesting and fun read, and it was a pretty short book, but that's where that reference comes from. 42 being the answer to all life's questions. The other approach that I could take, if I wanted to do this all in one line, I don't particularly recommend this, but I could use parentheses. I think simplicity is usually preferable to complexity, but I could increase complexity a little bit, do this all in one line. If I put that whole numerator in parentheses, then divide by 7, that forces the addition first. I get the same answer. So either way that I do it is fine. I just want to be careful that I don't omit the parentheses and try to do this all in one line. Okay, now, next thing I want to really think about is units here. As a math guy, I like to avoid units as much as possible and annoy all of the physics and chem folks who love units, but we probably ought to think of units. So the actually in Brandon data, this 5, 8, 11, 14, these kind of carry implicitly a unit of returns per day. So this 7 is really like 7 returns per day, or the 14 is 14 returns per day. What unit do I end up with for my mean? Well, in the numerator, all of my things I'm adding together have units of returns per day. In my denominator, n, the sample size, is just a counting number. That's just a number. It's unitless. If I add things of the same unit to one another, if I have 3 pounds of stuff and add 5 more pounds of stuff, I have 8 pounds of stuff. So when I add stuff with the same unit, it keeps that same unit. And then when I divide by a unitless quantity, I keep the same unit. My mean is in the same units as the original data. That's pretty good, right? Because if I want to know what the typical data point is like, or the typical data value is like in this data set, I probably ought to report that in the same units that my original data set is in. If I said, what's the average height of people in Pittsburgh, if all the measurements were in centimeters, and then I tried to report to you some number and just that ended up being in, inches or feet or something, that's going to be more confusing, right? So the mean has the same units as the original data. And same thing down here. Note that these salaries were in thousands of dollars. I don't have to go over to my calculator and do like 25,000 plus 28,000. Like, I don't have to do all this typing. I can just carry that unit of thousands through. This is a very helpful skill to have, especially a bit later on when being able to kind of think of, say, a percentage, right? If I have data that's like grade data, 30% and 28% and 14%. Hopefully those aren't grades, but whatever. But if I have data, being able to think of that percent as just a unit that gets carried through, rather than turning all those into like 0.3 and 0.25 and 0.14, like that's just more annoying to deal with. So this is in units of thousands of dollars for the 25 and for the 28 and for all of these. Again, my denominator is just a counting number. It's just a unitless number. So that unit is carried over to my 42, my mean. My mean salary is $42,000. The mean returns for Ashley is 8 returns per day. For Brandon, also happens to be 8 returns per day. Any questions so far? Okay, looking at the median now. So what is the median? It's kind of the middle number in the data set. Or the median, it's kind of like the middle data value. Very importantly, I'll put 2 underlines and 2 exclamation points of an ordered data set. I mean, if I just measure a bunch of random people's heights, they're all going to be jumbled up when I list them. I don't want to just pick like the middle one from that list. Like that has no real meaning. That's essentially random, right? Whatever the middle number is there by random sampling. It's just whoever I happen to choose as the whatever 500th or so person in my sample of size 1,000. But if I order the data set according to some value, so that means I need to have at least ordinal data here. If I order the data set and then I pick the middle number, that's a little more meaningful. That's kind of the height where, like, say, roughly speaking, half of the people in the sample have a height below that, and half the people have a height above that. So that's kind of meaningful. There is a computation in the book that you can use. Oh, with subscripts and all this kind of stuff. I don't particularly like that. I think it's easier to just do what we're going to do here. So let's go through each of these and compute the median for each of these data sets. Okay, so the first thing I want to do, we'll put exclamation point here. Ashley's data set is not ordered yet. The first thing I want to do before I do anything else, I want to write it in order. 5, 7, 8, 9, 11. So I've ordered it smallest to largest. I want to find the middle number. How do I go about doing that? Well, once I have it ordered like this, there's a smallest number and a largest number, right? There's a data point with the smallest value, a data point with the largest value. I just kind of cancel both of those. Not like forever. If I was going to compute the mean, I put them back in, but just for the purposes of this calculation. I have some more data. I have a smallest and a largest. I cancel those. And I'm down to where I have only one left. That's the middle number. With a data set of size 5, it's easy to just look at it and tell what the middle number is. But if you had a data set of size 51 or something, it would be a little more challenging. And doing this kind of crossing out from the ends makes it go a lot quicker. So the median for Ashley is 8. And what unit is carried with that? Well, it's just all that I did is I pulled the value right off the data point. It just carries its unit along with it. Returns per day. As an aside, the median doesn't get a fancy notation system like the mean most of the time. It's just median like this. You will occasionally see more in like mathy books than real stats books. You will occasionally see the letter eta, a Greek letter that's something like a long E kind of Greek, something like long E. the pronunciation of it has changed a lot over 2,500 years. But you will occasionally see this used for the population median, but I don't think that's a very common notation in the kind of stats side of things. It's more in like the mathematical statistics side of things. But just in case you're looking around and you see the symbol, you kind of know what it means, like how to say it and so on. Okay, so that's the median for Ashley. For Brandon, we do the same thing. We order first 3, 5, 7, 11, 14. Cancel one smallest with the largest, next smallest with next largest. If I go any further, I don't have anything else to cancel. So the median for Brandon is actually 7 returns per day. Ashley and Brandon had the same mean number of returns per day. That one way to answer the question, what does their typical day look like, was 8 for both of them. A different way to answer the question that seems pretty similar. We get the same answer for Ashley, but a slightly different answer for Brandon. So 8 versus 7 now returns per day for their medians. Now salary, I'm going to make a little change here. I'm going to get rid of one of these 28s just for the time being, so that I can demonstrate something really quickly. So this is kind of a, the salary data that we're going to use, but just for this part of this example. So if I order this, I have 25, 28, 28, 30, 55, and 100. Now let me do my same thing as before. I cancel a 25 with 100, smallest with the largest. I have 4 data points left over. I cancel the next smallest with the next largest. But now I have 2 data points left over. If I keep canceling, I have nothing. If I don't cancel, I have 2 things competing to be the median. What do I do now? In the case that my data set has an even number of data points, the median for this kind of, let's call it salary total, this adjusted salary data, its median is going to be the average of the middle 2. Now, again, when I take an average, this is thousands of dollars. This is thousands of dollars. My result still has that same unit as the original data. So a median for this kind of changed up slightly salary data is $29,000. If I have an even number of data points, I average the 2 middle ones. If I have an odd number, I just pick the middle one. So now if I put the 28 back in, what's the median for the actual salary data? This is kind of like parenthetical, what to do if we end up with an even number of data points. I can't find a way to come up with 3 data sets that each have nice characteristics for all of the things I want to talk about in sections 1 and 2. So, but the median for the whole salary data, because we'll be using this in a couple minutes here, there are 3 28s. And in this case, cross 100 off with 25, 55 with 28, 30 with another 28. In this case, I have an odd number of data points. I'm just left with 28 in units of $1,000. So just so I don't kind of forget later on, I'm going to actually cross this out. That was just an example for what to do if you have an even number of data points. But just so that when I'm referring back, I don't grab the wrong one, I'll cross out that one. And this is the median for the original salary data. Any questions so far? And then let's look at the mid-range. The mid-range is the average of the extremes. So where the median is kind of the average of the middle number or numbers, a number is its own average. So the median kind of averages the two middle numbers or just the one middle number. The mid-range averages the extremes. The mid-range is, and it doesn't get a special notation, just MR. It's x1 plus xn over 2, provided that we're ordered properly, or it's x min plus x max. It's the minimum data value plus the maximum data value over 2. It's the average of the extremes. So the mid-range for Ashley, her lowest value is 5, highest is 11. That's 16 over 2 is 8 returns per day for her mid-range. Brandon has 3 and 14 as his min and max data values. 3 plus 14 over 2. That's 17 over 2, that's 8.5 returns per day. And the salary data, 25 to 100. So that's 125 over 2, that's 62.5. And that's in thousands of dollars. Okay. Any questions so far? Okay, so I think what I want to do at this point is jump over to Excel. Let me shrink this window down just a little bit. I want to jump over to Excel to this chapter 3 demo, this one that looks like this. And I'm going to go to this tab. You see the tabs across the bottom, the one that says data sets for class. I guess I can just snap this to the left side, right? No, because I have two screens up. They filled like the entire top bar with stuff now, so it's so hard to grab any of these windows anymore. I don't know if this is just like me getting old and like, the kids these days and their crazy toolbars or what, but like anytime I'm trying to click and drag a window, I end up clicking on some sign into your account thing, or do you want to search for something, or do you want to rename the file, or they give you so little real estate, especially on like Chrome. If you have a bunch of tabs open and there's not like that nice big blank area on the right side on the top, like trying to find that little sliver to grab it and move the windows is kind of challenging. But anyway, we're looking at Excel here. We did the crash course in Excel last time. If you want something more structured, there's the free Coursera course you can audit. You can obviously, work through the exercises in the book, or you can just Google like, Excel compute average or something, and you're going to find a lot of good resources. So, or of course, you can always pop into office hours, email me questions, whatever. So you're not expected to come into this course being proficient in Excel, and you really don't need a lot of proficiency in Excel for this course. Just these kind of couple little things here and there that we're going to be using. Okay, so let's compute our three measures of center for our different data sets. So for the mean, I can do equals average. The Excel function that computes the mean is called average. So equals average. And then I will select the data that I'm interested in, say Ashley's data. And I see I get an average, a mean of 8. So equals average, open parentheses, click and drag to select the data, close parentheses, hit enter. You should get 8 here. Now I might want to be a little slicker. I know that I'm going to be using this data set over and over again, and I've already kind of renamed it Brandon up here. So if I hadn't renamed it, I might go up here, rename it Brandon, so that I can refer to it and not have to keep clicking and dragging and maybe make a mistake with one of my clicks and drags. And then I'll do the same thing with salary. So salary over here, I'll select the data set and I'll name it salary. Oh, it didn't like that. I already have something named salary. All right. We'll call it SALDAT, I suppose, salary data. For some reason, I had already named these blocks as salary. I forget why I might have done that, or maybe I made a mistake and saved this when I shouldn't have, but we'll call this salary data, SALDAT. So now I can refer to these equals average. I do see that as I start typing average, the average function pops up. Excel is saying, hey, is this the one you want? I can just hit tab and that'll put it in for me. So if you forget that, no problem, you can just type it out. But if you see that the function that you're looking for pops up, usually the more common functions pop up pretty quickly after you type a couple characters. You can just hit tab and it'll fill it in for you. And then again, I start typing Brandon. I see that the Brandon data set is selected. I can hit tab and it selects it. I see my box there, it looks good. I see Brandon's average is also 8. And again, if I do equals average, and I'll use this crazy salary data, SALDAT, computing the average of the salary data. I can do the same thing with the median. Note that I've put these in order here. Salary is actually top to bottom, but you don't need to have these written in order for Excel to know how to compute the median. It will do the ordering for you behind the scenes if you haven't done it already. So if you're ever bringing data over from, say, my stat lab into Excel, you don't need to like manually go through and order it, or even go to something like data and sort and order that way. Excel will do all of that kind of sorting and ordering work for you within the median function. Speaking of the median function, it's simply called median equals median. And again, I can click and drag, or I can click, hold shift and click again. Lots of ways I can select these cells. And parentheses. And I see actually has a median of 8, as I would expect. Oops. Or the Brandon data equals median of, and I start typing it in and there's Brandon comes up. So I just hit tab. That selects my Brandon data for me, and parentheses. And that gives me 7, which is what I expect. And then for my salary, same thing. Equals median of salary data and parentheses. And there we go. Any questions so far? Everybody following along with this? Okay, now for the mid-range, unfortunately, Excel doesn't have a mid-range function. The mid-range is actually kind of an odd measure of center, and we're using it for a specific reason that we'll look at coming up probably next time. But it's not a very commonly reported measure of center, so Excel doesn't have a built-in function to calculate it. But we do remember that the mid-range is the average of the extremes. It's the minimum plus the maximum, all divided by 2. So I could compute, say, the minimum of a data set by equals min of that data, and I see that returns the minimum. Equals max returns the maximum value. So what do I want? I want max of the data set plus min of the data set, or min plus max, all divided by 2. So I want equals. Now I want the sum of two things divided by 2. So I better use a parentheses here. So if I was doing like 3 plus 5 over 2, this will give me 4 and not 3 plus 5 halves, right? So I use my parentheses. What do I want to put in the numerator? I want the minimum of the data set plus the maximum of the data set. The minimum is calculated as min of these cells and parentheses. So inside of that first parentheses, which Excel is colored black, we have min of, and then we see the red parentheses. These are the ones that are the input for minimum. Excel has colored those red to help us keep track of how many parentheses we have open and closed and where they go together and so on. So I want min plus max. I want the maximum of this data set as well. I close my parentheses on the maximum. And then I close my parentheses overall. When I do that, I should see the black one at the beginning flash as well, indicating that I've closed off all my parentheses. I've isolated my numerator, and then just divide by 2. And that gives me 8 again, which was my mid-range for Ashley. That looks good. Let's go through that again for Brandon. I want Excel to calculate something. I type equals. I have a complicated numerator. I need parentheses around the numerator. I want to compute the minimum of the Brandon data. So minimum of Brandon data, I close the parentheses. That is all one idea now. Find the minimum of what? Of the Brandon data. That's what the min in the red parentheses all represents. To that, I want to add the maximum of the Brandon data. So this all represents one idea. Another number, the maximum of the Brandon data, will end up being 14. That's my numerator. I want to close my numerator parentheses. So I see that I have the 2 black parentheses matching that whole numerator now. The parentheses are closed and divided by 2. And as kind of a side note, if this is a lot for you to think about all at once, you can do something like this. Equals, just say 1 plus 3 divided by 2, just as like a placeholder. There's 1 plus 3. Okay, that seems to have worked okay. If I double click on the cell, if I click on a cell, it just selects it. But if I double click on it, it gives me the formula. Oops. Or I can also see the formula up here in the formula bar. So up top here above, like where the B and C column headers are, is the formula bar. I can see the formula up there when I just click on the cell. But I typically double click on the cell, and that's a little easier to work with, I think, most of the time. And then I say, okay, what do I want in my parentheses in my numerator? I erase the 1 and I replace it with one of the things that I want. Minimum of the Brandon data. That's what I want to be the first term in the numerator. And I could even hit enter here and just make sure that it works, that it computes and doesn't, like, crash anything. I didn't miss a parentheses or anything. And then what do I want as the second term in the numerator? the maximum of the Brandon data. So I can build up a formula component by component if I want, if it's getting a little bit complicated. Oh, I said Brandon, I was still on the wrong data set. We want the salary data now. Sorry about that. But there's our 62.5. So if I have a more complicated formula, I can kind of start by fleshing out a piece of it, just with kind of dummy numbers in it, and then go in and change things piece by piece to get it to where it needs to be. Okay, are there any questions on anything so far? All right, so I kind of mentioned I'm not feeling too great today, so I think I'm going to call it there. I think this is a good breaking point. Next time we come back, we'll take a look at the relationship between these three measures of center we've talked about, how they relate to skewedness, and we'll continue on with some other measures, starting with the mode, the weighted mean, and I'll probably actually just post a supplement on the geometric and harmonic means. So we should finish up 3-1 next time and get a pretty good start on 3-2 next time as well. And we'll, of course, talk about those means, both the weighted mean and so on, in Excel, as well as doing them by hand. Are there any questions before we break for today?